We are very happy to have Sumiran Pujari visiting us from IIT Bombay. And most of you know Sumiran. He has been doing extremely interesting work on various aspects of unconventional phases, spin liquids, and things like that. And he would be talking about his latest research in spin liquids and fabrication of spin liquids and exactly solvable models to this regard. Okay.
Thank you, Shubha. Thank you, and thank you everyone for coming. So today, what I want to tell you about is, if you wish, a new class of models, and you can sort of keep in mind models such as Kitaev toric code quantum Ising models as some backdrop. I'll be pointing some connectors to them. So the abstract title said some funny anti-commuting in some funny codes, quantum spin liquids, which have some residual ground state entropy. But the paper title, if you looked into it, is called Theorem on Residual Ground State Entropy, Quantum Spin Liquidity, and Related Models. So I will tell you why these funny quotes. But the use of word theorem means it is essentially simple enough linear algebra from a mathematical point of view. So it's a theoretical physics kind of theorem. I don't think of it as any mathematical theorem. So why are such things interesting to us? Generally speaking, not the physics thing, but having such exact statements. Firstly, they give us exactly solvable models, and so you can work things out in detail. But then there are these non-exactly situations where things are not exactly solvable. So examples would be Elitzur's theorem in gauge theoretic context, or even more classic example is Paulis' argument for why you can't have transition in the 1D classical Ising model. Okay, so these are kinds of exact statements which are not quite solvable models. And so what I'm going to talk to you about today is more in this setting. Those models won't be exactly solvable, but I will try to convince you that you can still make reasonably strong statements, okay, given the construction. And from a physics point of view, why it is interesting, I believe, is that it gives us the kind of physics that us as quantum condensed matter theorists, we like interesting. For example, residual ground state entropy. So the classic examples are, I should avoid this, classical spin ices. And another sort of non-spin fermionic example is the S5K. In some limit, it also has this residual ground state entropy. And we can furthermore prove in an exact statement sense that these models are also quantum spin liquids, okay?
It's only when n going to infinity.
Right. Correct. Yeah. That's what I'm referring. That's what I'm referring to. So there's a lot of density of states at the. So if you wish, the models I'm going to tell you is fine-tuned. So it has exact residual ground state entropy. But if you go away from the fine-tuning, I expect a large density of states in the many-body spectrum. Okay. So any other questions? Please feel free to stop me anywhere. So I will start by writing down the main result through this following construction. Okay, so consider the following model. On a square lattice geometry, we have qubits or spins at the vertices. Okay, and I draw a pattern. Let me write down the following thing: X, Z, Z, and this kind of pattern. We'll see why this is necessary. And then on the Z plaquette, you have a Hamiltonian term of the following form. This Z plaquette okay, like Ising model, standard Ising model, maybe with a coefficient Jz. And I might interchangeably use sigma or the quantum information notation where you use capital Z, capital X for Paulis. And by a very similar token on the X plaquettes, okay? And so therefore the Hamiltonian is sum over these plaquettes. And for the given plaquette, okay, we wrote the J mu there, but just for argument's sake, these terms, which with the mu index. Is it clear, the model? Right now along, but so thanks for asking that. It could include, the general statements will be valid even if you were to include this, okay? So let me first write down the two main results and then we'll have a look at the proofs a little bit. So the two results are, as I said, extensive, basically those two things. So in other words, extensive degeneracy for each eigenstate, many-body eigenstate. So it's nothing special about the ground state. Okay. However, this we'll point out the degeneracy counting. This degeneracy is not trivial in the sense that it's not a trivial paramagnet. It has a non-trivial counting. Okay, it's 2 to the power number of unit cells and not 2 to the power number of spins. Okay, so that's important. Even though from a mathematical point of view, the counting is simple enough. There's nothing complicated about it. And the second thing is the quantum spin liquidity statement. So if you want to compute some correlator in the ground state, and by ground state, I mean this extensively degenerate ground state manifold. There's an extensively large collection of ground states. You compute your correlator in that manifold, some equal mixture of them, two different sizes.
The number of degenerate states is of order n.
Right, order 2 to the power proportional to n. Yeah.
Okay. So
Yeah.
so you have extensive entropy.
Correct. You have a finite entropy density. They somehow loosely call it extensive degeneracies and sub-extensive degeneracies. Kind of. Yes. Yeah. Something like yeah. Exactly. So the statement is even at t equals to 0, such correlators are just 0. There's some cancellation arguments. I'll try to hint at it, which tells you that it has a quantum spin liquid-like property, these fine-tuned models. So this is one such example. And there are also, you can make exact statements for higher order correlators, like four spin terms and 4-point correlators. But I won't get into that today. Okay, if no questions, I will go ahead. So as we said, so why is this true? So let's first try to ask this question. So as Shubhro anticipated, there are some local conserved quantities. It turns out local conserved quantities, very analogous to Kitaev toric code or Kitaev honeycomb model. Okay, but they will have the way it will distinguish itself from such models is through this anti-commuting property, which we'll point out. So on the Z plaquette, recall Z plaquette has sum of sigma Z, I think terms. We have the following conserved quantity. So this commutes with the Hamiltonian. This is a simple enough exercise. Essentially, the outgoing links from the Z plaquette are sigma X, so it commutes. And on the plaquette, you have pairwise anti-commutation. So it's the same kind of trick that Kitaev honeycomb or this kind of thing. And similarly, by a similar token, on this, I have this as the conserved quantity. So I have this many number of conserved quantities. These are extensively many conserved quantities, similar to, again, Kitaev honeycomb model, for example, right? However, here's the new point. In Kitaev toric code or Kitaev honeycomb model, that actually are those conserved quantities mutually commute with each other. So they actually help you to reduce the problem, okay, into maybe some free fermion problem, maybe not. Here, actually, that's what is not going to happen. And the reason is as follows. So if you have this site sharing situation, on these two plaquettes, the conserved quantity shares a site, right? So therefore, they anti-commute because there's a single, right? So this product of, so I just wanted to mention that this is essentially the Z2 parity of the Ising chain, but on a small plaquette. In this geometrically site sharing situation, actually these two anti-commute. Okay, so it does not reduce like the Kitaev toric code or something. So more generally, Kitaev toric code, Kitaev honeycomb model, all these models, and more generally, there's something called the string nets, Levin-Wen models. You kind of almost from a model construction point of view, you actually want to avoid this. You want to have mutually commuting algebra of the local conserved quantities so that you can find some interesting properties such as many-body topological order. But it turns out in these models, that is just not true from the get-go. Okay, and now because of these, it essentially cares for these local conserved charges, the structure, it is relatively agnostic as to the form of the microscopic Hamiltonian. You can have different things where these are the local Z2 parities. If they're conserved, all of this will follow. For example, the other model where you put these bonds and so on. And even the magnitudes, this JZ, JX, these are also, it does not care for it, right? So this is what I mean by this anti-commuting algebra or structure. Okay, so I have local conserved charges. They anti-commute when they share a site in this particular construction, but more generally, somehow some subset of pairings anti-commute, and the rest, of course, commute. For example, I take the conserved parity on this plaquette and this plaquette, on this plaquette and this plaquette, they naturally commute, right? So this is what because it's not anti-commuting, every pair is not anti-commuting, I give this symbol, okay? And here there's an interesting sort of, my French connection is that when I was writing the paper, I started out by putting, English quotation marks, but that sounded funny for the paper, having English quotation marks everywhere. So this is actually French quotation marks, okay? So that was a good compromise for me too, in terms of notation. So it captures the spirit, that whenever this is a very geometric property. So in Kitaev toric code, Kitaev honeycomb models, the local conserved quantities actually share, pairwise share sites. So therefore the commute. Here just a site sharing is happening, so it anti-commutes, okay? So just having this structure actually immediately leads to this through some linear algebra. And the linear algebra goes as follows. Suppose you have a conserved quantity A, and you have another conserved quantity B. So this is very much like, imagine, S square Hamiltonian for a single quantum spin. And they anti-commute. Then if you take an eigenstate, which you have to choose which basis to work in. So let's say you choose this one. Then it's a few steps of algebra to show that this is minus A, B psi, but the same energy. So this B psi is degenerate with psi, but the quantum number under A has changed sign. And all the models that we consider, this A is either +1 or -1. So it has to be a orthogonal state, okay? So I hope this was Clear? So if you give me this, then the A and B are all these conserved quantities. Okay. So I will choose. So I have to choose. So I have to choose a set of conserved quantities which are all mutually commuting. So I can choose all the Z plaquettes maybe. And then I have no freedom to choose the X plaquettes. And then you write down your eigenstate as whatever conserved plaquette parity on these Z plaquettes, say +1 everywhere. Then you act with one of these, conserved this X plaquette operator. You will change the, this A eigenvalue locally. You start generating new copies. Yeah. So that's a linear algebra. And you can see that you can act the analog of B at many spots and multiply, right, in the lattice. So you get 2 to the power, however many X plaquettes are there, not the number of sites. So the counting is simple, but non-trivial. Okay. So in this case, the counting is just the counting of one of the set. Is this maybe I can pause for 5 seconds. Do you have a question? No, sure. Okay. So you just have to count the number of one of the one of the sets, right? And it's clear you can do the counting. All of us can do the counting. So that counting gives the degeneracy for each eigenstate. Remember, there's nothing special about the ground state here. So it is true for the full spectrum. Okay. So whenever you have this anti-commuting algebra of local conserved quantities, the many-body spectrum, regardless of whether it is gapped or gapless in the sense we asked the question, each eigenstate, okay, will have this massive degeneracy, and the degeneracy is number of unit cells, it turns out. UC stands for unit cells, okay? Each unit cell is made of 2 such plaquettes, okay? Okay, so this is the first result. And this is already a little interesting, but the next statement is the following.
Let's say Z plaquettes.
Mm-hmm.
So if you start with another initial Z plaquette configuration,
right,
are they connected? I mean,
yeah, they're connected through the actions of the X plaquette operators. Yeah, there is some super selection sector business. So that's a good question. Suppose for some reason the value of the conserved quantity is +1 everywhere. Now, if you act with this, all these +1s will change sign. So you change at a go, modulo 4 or something. So there's a sectoring there. Yeah. Yeah. Mm-hmm. Mm-hmm.
let's say I start with 2 initial.
Of the Z plaquette.
One Z.
Right.
One Z.
R minus.
No. One Z is minus.
You won't. No, you can't get it.
Can't get it.
No. It's kind of like the global Z2 of quantizing model. Something like that exists. I've not worked it out in any detail, but that can always exist. That does not, void this property. Maybe. Yeah. So those kind of additional sectoring will exist in these models. I'm not paying attention to it. Okay. So this I won't prove it here.
It's in the membrane operator. Because you cannot change the parity of the down spins per row and per column. Right? So then the X operator is like a membrane operator, it just keeps. That's it.
Right.
Disjoint membrane.
Right.
It's the big.
Okay, so I won't be able to answer that question, but my point of view on that is, my understanding is generally subsystem symmetries don't go all the way down to the local level. They always try to be between d = 0 and the volume dimension. So I have some system. There might be some subsystem symmetries, but those subsystem symmetries are described by operators which don't have which are not 0 dimensional, neither the full, like global Z2 full dimensional. That's my understanding. So in that sense, these subsystem symmetry goes down all the way to d equals 0. So that is one sort of just observation. But from the fractonic point of view, my understanding is that all the models do not have, generally speaking, this. You still want commuting algebras. And then you can talk about rigidity in the perpendicular directions.
Take one of the Z spins to be down. I mean,
Okay.
not in the sector.
Hmm.
I think.
Hmm. Hmm.
Take one of those
Hmm.
spins to be
Hmm.
down.
Okay. Hmm. Hmm. Hmm.
If the X operator on that,
It flips.
so
You flip all the spins. Yeah.
the plaquettes,
Hmm.
you know, the parity of basically the down spins on the row and the column
Will also change.
won't change.
Because these two pairwise change. Yes,
Yes.
I agree. Yeah.
So then you can think about this X
Yeah.
as sort of this
Yeah.
membrane operator.
You can. Yeah.
You can either act it or not.
Yes. Yes. I agree.
And if
I
you
agree.
cannot partner, it would basically lead to constraint dynamics of these downs.
I'm not sure about that, but maybe. I've not thought about that because these are just the conserved charge operators. They're not some physical operation as such. So maybe what is the dynamics is not even clear because it's extensively degenerate. So suppose I want to just suppose I have some ground state, some state, some eigen.
Just with the next steps.
This one.
The next
True. But the point is the eigenstate won't have a well-defined downspin.
Yeah, this is not an eigenstate.
This is not an eigenstate. Yes. So you put some energy, maybe the energy only spreads in one direction. That is possible. I've not thought too hard about that. So yeah, so more generally speaking for the students, the transport property. So what he's talking about is how energy or spin will get transported. Suppose you inject doing this flip. How will it get transported? In fractonic orders, there is a very special directional dependence. The question is whether it is true here or not. I'm not sure. Yeah. Okay. So the way this works out is as follows. So first of all, what I mean by this is, let's say t equals to 0, is over all the ground states in the manifold. There's a full manifold of ground states. And I sum over all those. So this is what you would do in any equilibrium stat mech type of situation. Yeah, please.
We should calculate the degeneracy of each state.
So it is this. It is just this. So that's what I was saying. It's a simple counting. It's just a number of one of the sets. Yeah, you just do what you said. It's standard, linear algebra, block diagonalization of the Hamiltonian. Yeah. So the point is, if you take one member of the ground state manifold for this discussion, this summand won't be 0 actually, because there's no reason for it to be 0. But when you do this sum, you can prove that there are cancellations. That's the idea. Okay. So I'll just sketch the proof. So let's take one state. Right. So needs a little bit of setup. And again, I'm working with this choice of I want to organize my block diagonalization using these conserved quantities. Let's say this be I, this be j. It's not very sensitive to how far they are. So then so I'm interested in this correlation. So I'll maybe take this X plaquette. This X plaquette will play a role in the proof. And for this one, this X plaquette. So there will always be an X plaquette for any site, right? And you are interested in some correlator. So this is something, we don't know what it is. But now there are partner states given the states I and j, right? So I'll pay attention to special partner states. So what are those partner states? So this is the X plaquette corresponding to this site, and similarly this. So I'll just use a shortcut. Let me use a notation. So we'll call this, some pi of X. I'm just making a notation as we go along. So just excuse if I'm being a little sloppy. So we can create 4 possible states given those 2 special X plaquettes. So they would be, you act with the product of this particular conserved quantity for site I on psi and compute the same thing. Same operator, pi x on j psi and both. And so these operators are also on the other side. And now it's a matter of simple commutation algebra, and you will see that there will be some sign changes. So for example, let's take, for argument's sake, because we are acting with x, right? So x plaquette, sorry, I mixed up. So we are working in z plaquettes. So we wanted to act with this operator. So this should have been written there. So these notations get a little confusing, but I think you will get the idea. Now suppose this were, because these are product of z's, let's say there is x here. X, of course, anti-commutes with z, right? We have the simple relation that sigma z, sigma x, sigma z minus sigma x, right? So this will change sign. So this had some value. I don't know. This will have minus that value. This will have minus that value. This will have plus that value. So in the sum, they will just cancel out, okay? So using these z operators, I again mixed up my notation. Using the z operators, I can cancel out all possible combinations of mu nu, which do not, unless both of them are z. If both of them are z, then you will get a z here. And the cancellation you won't see in this way of organizing the calculation. But you could have started the calculate for the particular case of when mu equals nu equals z, you start in the other basis, where you start with the other set of the, and then you prove the cancellation. So for two-point correlators, it cancels out. And in the paper I've worked out for higher order correlators, they don't always cancel out. There are special values of mu, nu, rho, delta, which do survive. And this is very analogous to Kitaev honeycomb model, actually. In Kitaev honeycomb model, all 2 spin correlators are hyperlocal in this sense. They cancel out just right away. But the let's say bond correlator actually has a power law form, okay? And this property actually is quite, at least those don't cancel out. I don't know what are the non-zero correlator, higher order correlators doing, but you cannot use the cancellation argument to show they are 0, okay? Yeah, sure.
So I don't think apart from this, let's say there are all the jet buckets and the let's commutator of that. If I choose my basis for the energy and
Right.
But it seems like, let's say, if it's in a periodic for us, then product of all the x on a line. So it's like this one.
I'm not sure.
Because every jet bucket is acting by x twice.
So you want to say what is conserved? Let's say this line or this line. Yeah, this has only one kind of bonds. I agree.
So, yes, this is also a symmetry of the Hamiltonian that is Hamiltonian.
What do you mean by symmetry?
States, right?
You are saying that the product of all this is conserved. Is that what you're saying?
It also commutes with the
Yes, because it's just the product of these local things. So you just multiply these local things. Them individually are conserved. These are conserved, right? We are. Yeah, with the z, you are saying. Let me think. Which some particular z, because this and this commute with this. And this when this commutes with any z. That's a good point. Yeah, I agree. I agree. So this probably connects to what Shubhro is saying. Yeah. Yeah, please. Like numerically? No.
Because you have this plus, but if I change it to minus, that doesn't matter.
That does not matter. So +1 corresponds to having, let's say, even number of down spins. All up, spin up, right? Yeah, that is not a ground state. That is not an eigenstate.
That's not an eigenstate.
So what was the question?
All the x's, so equal superposition of that
could be.
Acted with this 1 plus x by 2 plus
Yeah. Something maybe. Yeah. That probably is the ground. That probably is the ground state. And then all the partners. That might be a way of writing it. Oh, great. Thanks a lot. Yeah. But just let me just. However, I don't still believe that it will be this loop superposition type state of stringlets. One needs to check the state that you proposed. Is it re-expressible as a loop superposition? It might be a generalization. Very nice. He wants to take a product. Actually, why don't you tell me? Sigma x, right? Everywhere. Because sigma x. Sigma
sigma x on this bracket.
Right.
Another bracket on this.
Right. But that is just a product of these conserved quantities, isn't it? So you want let me just do it. So you want product of sigma x, 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 right? This commutes because locally it commutes. But here, there's a single sigma that it does not come. Yeah, because this I had worked it out today morning, so I got confused. There's a single link going out, no? So it only cares for what is the entry on this side. But it will connect. I'll answer your question. Yeah, I got confused about this. There's a small mistake related to this in my paper, and which I realized this does not commute. I'll already give you a teaser. But as I said, this microscopic structure is not like these two follow more generally. So you could, instead of taking these 2-spin microscopic terms, you take 4-spin microscopic terms on those plaquettes. Product of 4 sigma z's and a product of 4 sigma x. Then what you're saying will become true. I know what you're thinking. That is not true. That's not true. That's not true, as he pointed out. Yes. Correct. Yes. Right. You want a product of sigma z's on this. Sigma x, sigma x, sigma x, sigma x, sigma x, right? But it anti-commutes with this because there's a sigma there. No. It's a sum of these terms, the Hamiltonian. So you have to. Yeah. But you got the point, right? No, it's fine. I also got confused. However, the deformation where instead of the 2-spin term, you take the product of 4 spin terms on the plaquette, that will become, So this will connect. So this, now I believe this particular model does not have toric code like topological order, but that deformation, which I'll show anyway, if time permits, does have topological order, and this is one way of seeing it. Okay? Yeah. But Shubhro, we should chat. Yeah. No. We'll talk about that. Don't worry. Don't try to do the calculation. I am supposed to do the calculation for you guys in this lecture. If it was a class, I would have stopped and actually let my students, calculate for 5-10 minutes. Okay, so where were we? So the cancellation argument, I hope, is clear. And actually, all possible combinations of mu nu for 2-spin is actually cancels out. Higher point order don't all cancel out, and there might be something there. Okay. Okay, so now actually we are already, so these are the two main results of the paper. Rest is all discussion. Okay, so we'll see how long that goes. Any questions about, yeah, right. Yes, yeah, because of this. Yes. No, for any, so let's take your example. So this is J, right? This site J में sigma z है. So the site I में है, right? So this actually anti-commutes with this. So you get a minus sign. In this, you have Z on J. So maybe this becomes plus and maybe this becomes minus, something like that. Okay. So the cancellation goes for all possible two spin. Yeah, you cannot start from this choice. There you start the argument with this as the block diagonal basis, but the correlator is basis independent, so you don't care. Okay, very good. So now I will try to compare and contrast to all the stuff that I know and try to give you a sense of why I feel this is like a new beast. Okay. So let's maybe first compare it to, so the most natural thing to compare it to, so maybe let's first mention some deformations where it will be true. So one is this kind of thing. First of all, the coupling constants are not important for the discussion. Then, so what these guys are specifying is the local microscopic spectral structure, meaning that the JZ value, JX value can be different from plaquette to plaquette. And yeah, the same. Yeah, translational symmetry is not very important for all of this. So there might be, from the transport point of view, you can still get glassiness and stuff if you perturb away from translational invariance and so on. Okay, the next one is, so we can write down, so so one point I would like to mention is that here the degeneracy counting was very simple, okay? It's just the count of, well, you make your choice, the other set gives you the partner states. So whatever is the count of those other states gives you this, right? The count, degeneracy count. But doing that counting itself can be, trickier a little bit if it is not this simple square lattice structure, and there is one more elaborate structure, lattice structure in the paper where the counting, there is some, if you wish, subtleties which I've pointed out. But this is a very nice prototypical model to focus on actually. So given this anti-commuting structure or algebra of the local conserved charges, these are essentially local Z2 parity of small Ising chains. So another way of thinking of it is you have these Ising chains and you've cross-linked them. So this is an Ising chain in the Z direction, this is an Ising chain in the X direction, and you've sort of cross-linked them, right? So here I'll give a point of comparison. So let's take the Kitaev honeycomb model. So Kitaev honeycomb model is, I have this XX, YY, ZZ structure, right? So maybe this. So actually you can compare this kind of model construction to the Kitaev honeycomb model. So what did we say here? We have these small plaquette-like Ising chains in orthogonal directions, X direction and Z direction, and I've cross-linked them. If you look at the Kitaev honeycomb model from that point of view, you have small Ising bonds, okay, which you have cross-linked in orthogonal directions, okay? Now, the Kitaev honeycomb model, of course, as we know, has commuting algebra for the local things, but this commonality is there, that you have small Ising units which you are cross-linking in orthogonal direction, and that gives rise to some liquidity, okay? However, what is the exact detailed physics? But this is a much more general structure. there is a lot of variety you can have at the level of the local microscopic units, right? So I want to point that out. So one is this, what we wrote. We have small Ising chains, okay, small Ising chains, Ising plaquettes. So what is the spectral structure of this? Suppose it's just ferromagnetic or something. I have 2 ground states. I have maybe 4 or 8 excited states, maybe 6. And these have the gaps proportional to the coefficient here, right? So here there are only 2. I could do what Kitaev was saying. I could also have these. So this is like a 2D version of the pyrochlore lattice. Not important, but imagine these links are there. And if they are all, so here it turns out this spectral structure does not care whether the sign is positive or negative, whether it is ferromagnetic or antiferromagnetic. You know that they are almost morally the same modulo the thing that we were discussing about. So when you have antiferromagnetism, there can be additional, the translational symmetry properties are different than ferromagnets. There's some consequences, some anomalies, which I don't understand, but Shubhro was telling me yesterday. But now if you do this, then if you have ferromagnetic sign of the coupling, it goes back to this. But if it is antiferromagnetic, then you have actually 6 states. And then some, so there are a total of 16 states. They're divided in some fashion. So for small Ising chains, unfrustrated Ising chains, you have 2, 4, 6, 4, 2, something like that. If you have a pyrochlore antiferromagnet, you have 6 ground states and some structure like that, okay? So, and let's take this case, which I'll discuss more later, which is this 4-spin variant. You know, it's a product, it's a 4-spin term. This is now, by construction, a plaquette parity variable. So this has actually 8 states. So these microscopic spectral structures will actually inform the final macroscopic physics of the many-body spectrum, but remaining consistent still with these 2 properties. There can be some sub classification of those many-body eigenstates, but they will be liquid-like, and they will have residual entropy, okay? Okay. So this is one, so the point of contrast I mentioned with respect to Kitaev honeycomb model, right? So this is kind of, you see, Kitaev honeycomb model we know how to solve, right? That's one fascinating aspect of it. And we know that there's a unique ground state or maybe finitely degenerate. There's no extensive degeneracy. There is a lot of low-lying eigenstates due to the, when you change the flux, plaquette flux numbers a little bit here and there, you get a lot of states, right? But it's not degenerate. Here by construction, because of this anti-commuting structure, remember in Kitaev honeycomb model, we only have a commuting structure of the local conserved charges. You get this, okay? Very nice. So the other point is, another point of contrast. So now I will compare it to Kitaev toric code. So actually, so for Kitaev toric code, maybe it is slightly better to keep this 4-spin variant in mind, because the 4-spin variant has a very natural family resemblance to the Kitaev toric code Hamiltonian. So let's recall what is the Kitaev toric code Hamiltonian. So the usual way, or let's say in Kitaev's original paper, if I'm not wrong, you put the degrees of freedom on the bonds. And then you specify your star and plaquette terms, right? So the star term is maybe product of, literally x's. I was trying to demarcate them. And the plaquette term is Because of the construction of the model, these are 4-spin terms. They share pairwise, right? But if you just look at it from a slightly different point of view, this rotated point of view, they also actually sit on a square lattice. And then you can sort of compare what is the Hamiltonian term specification difference between the two. So in that sense, there's a family resemblance between them. However, if we do this, so what is the Hamiltonian? Now we look at the 4-spin Hamiltonian. The 4-spin case. So we have our mu plaquette. On the mu plaquette, I have my 4 sites. 1, 2, 3, 4. But by construction, here you see there's a pairwise site sharing property. Here there's a single site sharing property, right? So this model satisfies. And then you can ask, how does it compare to Kitaev, toric code, or whatever? What is going on? So for here, we can make some additional statements, it turns out. So I'll try to do that. Any questions? Okay, so the model definitions is clear, right? So what is this? So firstly, I'll show you a very nice. So there are 2 arguments. So of course, all of this has this extensive degeneracy and liquidity. But having said that, like some of you were trying to see if there is some super selection sector business happening or not. So whenever there is a super selection sector business happening, you may think that there is some many-body toric code order, okay? Because those are essentially some non-local super selection business, okay? So we'll do that. So it turns out that the punchline for this model is going to be that even though it is liquid-like in this extensively degenerate sense, there's an underlying many-body toric code topological order. This we can work it out. And we can work it out in 2 different ways. So I would like to show one nice argument for why you have topological order in this one. Yeah. So this argument is by, at least I have seen it, Ji Chen. She's from Caltech. There are a bunch of lectures on many-body topological order on ICTP. Okay, you can find it on YouTube. And it's a very neat argument. Of course, you can prove topological order using what Kitaev told us, right? So the way to think about it is, so, and it will show like how this anti-commuting structure is fundamentally different than the standard commuting algebras that you have in Levin-Wen or known many-body topological orders. So we have our conserved quantities. It turns out very analogous to this, the conserved quantities are the star and plaquette terms because they mutually commute, right? So the way you can now make progress, one way to make progress without actually, so what you say is that whenever you have a conserved quantity, which is 2-valued, that implies your full Hamiltonian breaks into 2 big blocks, right? Now we have many such quantities, right? I'm not going to explain all the details. It needs a little bit of bookkeeping. So we have all the plaquette terms which will do this block diagonalization for us, and all the star terms which will do this block diagonalization for us. So how many plaquette terms and star terms are there? As many unit cells exist, right? So, okay, let's do the counting. Let me try to see if I can do it. So what is the total Hilbert space dimension? It's 2 to the power number of sites. Equals 2 to the power number of bonds, because there's a site per bond in Kitaev toric code, equals twice number of unit cells, because there are 2 bonds per unit cell on the square lattice. And now we have to count how much block diagonalization the mutually commuting structure gives us, right? So there are n a number of unit cells, number of plaquette terms, and number of unit cells, number of star terms, right? So now you do it. Now you do this block diagonalization. So every time you do a plaquette term subdivision, you reduce by a factor of 2, right? So how many are there? Plaquette terms, unit cells, and how many star terms are there? Sorry, for the experts, they probably know this argument, so I might be boring them. Again, the same number, right? Number of star terms. So what is the answer? Huh? Please? Correct. Which, is it correct? Okay, let me tell you, it's not correct because it's toric code order. There should be a degeneracy of 4 if it is on a torus. Let's say we are on a torus because that is important. So how do you resolve this? I'll tell you the answer in interest of time. Not all the plaquette terms are independent of each other. Not all the star terms are independent of each other. If you multiply all the plaquette terms, that's identity. So the final block diagonalization you are not allowed to do, both for the star terms and for the plaquette terms. So therefore, the degeneracy of 4. Okay, so it's a very neat argument. You can try to do the same argument here, but because of this anti-commuting structure, you stop at the count we arrived at. You can't do more than that, it turns out. Okay. However, we don't have recourse to such arguments for these models. However, now what I'm going to show you is that there is indeed many-body topological order in this model. Okay, and this is connecting to what you were saying. So another way of seeing this global, this fourfold order. So what I want to say, so where is the intuition coming from? The intuition is coming from that it is liquid-like, right? So therefore, there is no standard Ising order, which is similar to toric code order. Toric code order also has no ordering, right? It's unordered, but with finitely degenerate states. Okay, so here's another point of comparison. So maybe I write it here. So take a partner model of this. It's called the 90-degree compass model. Again, you have Ising chains, but these are literally Ising chains. So here we cross-linked Ising plaquettes. Here we'll cross-link Ising chains, but in orthogonal directions. So this is Ising chain in X direction, and these are Ising chains, let's say, in Z direction. Okay. Each Ising chain again has its global Z2, chain Z2 global parity that each one has, right? Everyone is okay with me? The product of sigma Z's on this commutes. Product of sigma X on this commutes. However, because of the non-local nature of the conserved charges, if you do this linear algebraic argument, actually you find out that there's a degeneracy of 2. You don't get extensive degeneracy because they are non-local conserved charges which cross-link. Okay, here we have local conserved charges which we are cross-linking. The non-local conserved charges here, the global, like the chain Z2 parity, global Z2 parity of the chain, are also anti-commute. So this has the anti-commuting structure. However, so I did not emphasize it enough. For all of this to be true, you need extensively many. You need this local structure in the conserved charges. So that is where it connects through the known string nets and all that. And this is fairly intuitive that depending on the value of the coupling, it will have Ising order either in the X direction or in the Z direction, right? However, we know to begin with that there cannot be any Ising order, any magnetic order in our situation, right? So, but this, but it turns out, so even for Kitaev toric code order, apart from this kind of counting argument, you can define these global Z2 symmetries, which is another way of seeing the degeneracy of 4. Okay, such global Z2 exists here, but did not exist in the discussion we had. The 2-spin variant, but it starts existing in this 4-spin variant. So this gives you a sense that there might be toric code order riding or coming along with this property. So there's a liquidity due to just this extensively degenerate manifold. Okay. However, underlying there might be a toric code order, and we'll be able to prove it without exactly solving it. Of course, it was a very interesting remark that you made that maybe there is a formally exactly writable in the spirit of Levin-Wen string nets. It is not, but the formal solution as you propose might, yeah.
What it means is that if I add small perturbation, there's this huge degeneracy.
Yeah.
Gets lifted.
Yes.
And on a torus, only 4 survives.
Right. That is a check one has to do. I'll give you an argument for why you expect it to survive. Okay. I'll give you an argument right now, but that is my expectation. But you can check it.
The degeneracy in toric code has nothing to do with subsystem symmetries. Split all kinds of symmetries and still itself. The argument that you seem to give.
This counting argument?
Yeah.
That is also.
So it depends very strongly on the structure of the local terms.
Okay. But not the coefficients, but yes, the local terms, yes. It just needs existence. It just needs the conserved charges. And then, yeah.
So that's very different.
Right.
Looks like some short distance physics.
Right.
So,
I understand what you're saying. Yeah. So if I'm claiming there is a global many-body topological order, where is it? That is, yeah, it's not evident. So I'll show it. I'll give the argument. It's not exactly solvable, except in this formal way, which might be right. So it's very interesting. The other thing that I can mention, the side comment, not very interesting, probably, is there's something called the Haas bound. So there's a bound on the degeneracy. That any many-body, my understanding, topological ordered state. So this includes subsystem and fracton-like things. The claim is that for a certain class of many-body topological order, this degeneracy cannot be extensive or this finite entropy like. There has to be sub-extensive in that sense. That's the statement of the. So if I show you that there is some topological order, this would constitute at least an in-principle violation of this bound for whoever finds that interesting. Okay, so why is this topologically ordered? Why are we saying this?
Let's say that if you have the entire length, then you can always rearrange your basis to write down 1 year.
Possibly. However, I am getting these infinities for free. Given once I have this structure.
Okay.
No, extensive, 2 to the power number of unit cells. This region. This one, right?
Yeah, number of spins.
Not number of spins, of course. It's not fully trivial, but it is not sub-extensive either. It is extensive, but fraction of the volume. Yeah. Okay, so let's make that statement. And you will kind of, so that is why I went to do this, pointing out the local microscopic structure is somewhat important. Okay, so for this particular 4-spin model, we will show or we'll give an argument for why you expect many-body topological order. Of course, what you should do is what Shubhro is saying, you just put it on the computer. You should see that additional degeneracy of 4 on the torus after you factor out that extensive degeneracy. Either you actually literally factor it out, or you go away from the fine-tuned point, you split that degeneracy, and then you still see a remnant. So just a side remark that in the paper, so this is not solvable as I understand solvability, but in 1 dimensions, you can construct some solvable models. I'll give a remark at some point, and you can see how this splitting works. You can work it out and you can build an intuition. But the perspective is that any physics that is, any temperature scale that is above those splittings should see this physics, the standard statement. Okay, so let's move ahead. So we are now considering this 4-spin model. So I'll just write it down again. for completeness. And it's a two-line argument, really. Maybe for this quantum notation is better, actually. With some coefficients. We are agnostic to that. The model specification is clear, very much like the Kitaev toric code model. Now, of course, it will, again, these are the conserved quantities, and therefore these are true. Okay. So on Z plaquette, it's the product of x's which is conserved, because the product of x will commute with all the neighboring this, and it again has the pairwise even number of anticommutations. Now what we are going to do the following. Again, we are going to focus, we are forced to focus on one set of the local conserved quantities. However, this is where you have to keep in mind this structure. The Hamiltonian locally, the local microscopic terms have this structure. It has to be consistent with this. So what else can happen? Okay. So this suggests for the many-body spectral structure in the sense of the values of the eigenenergies, right? Not the spin configuration. The spin configurations, I already know that they will undergo cancellations. But the energies, for energies, what can happen? For energies, you see, it does not care what is the underlying spin configuration on the plaquette. Yeah, please. Yeah.
Is this Hamiltonian continuously connected to the
I don't think so right now, but I could be wrong. I believe there is a further sort of phase diagram within this class.
There is no one mapping of the second.
That I don't know, but like all the models satisfying these anti-commuting structures, first of all, there can be more elaborate anti-commuting structures, but even for the square lattice situation, all anti-commuting Hamiltonians or there will be some finer, not finer, some underlying classification of some with many body topological order, some with maybe non-topological order. I don't know, but that's my hunch. Yeah. Yes, please. The same. This plaquette? This one? Yeah. This one? Yes. Yeah. You're right. You're right. So you take the product of what? Thank you. That's an important comment. I've not thought about that. That is indeed conserved because there's pairwise commutation. I'll have to think about it. It will do a further block diagonalization for you, which I've not paid attention to, but this still is there. You cannot get rid of this, I don't think. Yeah, there will be further block diagonalization, and yeah, I've not thought this through, so we can discuss. Certainly, that's a good, I have not thought about this. So now I want to analyze this. So if we forget about those new conserved quantities that you pointed out, this suggests, because I am trying to understand, let's say, the energetics. So I don't really care about the spin configuration, the spin state of the plaquettes. For the energy, I just need to know what is the parity, whether it is one of this or one of that. That will control the energy, right? So this suggests that you do like a Kadanoff block spin thing, okay? And only one step, okay? So this is the key insight. So if I'm interested in the energetics, I actually don't need to pay attention to the spin state. I just need to pay attention to the plaquette parity, right? So I'll define this variable. There's a reason to give it this name. I'll define this variable, this two-valued variable, which takes, it's like, think of it as Kadanoff block scaling. You kind of coarse grain and you just look at the plaquette parity, nothing else. So this two-valued variable just tracks for you whether it is in the lower state or in the upper manifold. Which manifold exactly? You don't care. You don't care even further because of this property. You know that it is relatively featureless, all these cancellations are going. But if you do that, let's say these were the Z plaquettes. And I'm doing this block spin thing. So then I'll have a new lattice. So on the Z plaquette, the tau Z is defined, right? On this side. Now this, remember it's a 4-spin. So this plaquette couples these 4 plaquettes, right? So actually this term is actually a 4-spin term in terms of the tau variables. Everyone? It must be a 4-spin term in terms of the tau variables also, right? Because this impacts the neighboring 4 Z plaquettes. So can someone like to, among the students, take a stab at what should be the, so the Hamiltonian, when you go into this tau language, you know what we mean, right? Right? This is a 4-spin term, we agreed on these, Z1, all these 4 plaquettes, Z2, B. But what should I put there? Anyone from the students, please? Kind of doing what I do in my lectures. So what does X do? What will X do to the plaquette parity? Change the parity. So in terms of the tau variable, it is tau X, exactly. So this is the effective model in the block spin variables. And this is a very famous model, it turns out, in gauge theories. It's called the Wegener's Z2 Ising gauge theory. Precisely. It's kind of like toric code. Yeah, except toric code, if I understand right, it's a product of tau z's. This is not. So this is not solvable. However, the belief or the understanding, the consensus is that this has same toric code order as the toric code itself. Okay, in when this dominates, this coupling dominates. So if you, but you see here, so this is kind of interesting. In the original, so this I have not thought this through. This mapping is a microscopically exact mapping. If you don't pay attention to the spin state, you pay attention to the only plaquette parity states. This is it. Okay. Now I'll little bit think extemporaneously because I've not thought about this. Of course, if I forget this and just someone gives me this as a spin Hamiltonian, then obviously when this dominates, this is not topologically ordered, right? It is just simple paramagnet. However, when we look at it from this point of view, actually there is no special reason to choose this over this. So then how do you reconcile? Here it seems, so the known statements are where when this dominates, or you have perimeter law scaling, when this dominates, you have area law scaling, blah, 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 blah. You can read Kogut's review. Fantastic review, and the anecdote or the fun story is that when Wegener in 1971 wrote the paper, no one, maybe you know this story, HRK, that when Wegener wrote this paper, no one understood it. And then it required Kogut to sort of more or less transcribe it for the rest of the community. And then everyone was able to. Of course, Shubhro probably hasn't read these papers, because it were pre-83. There was an inside joke with Shubhro. But yeah, so my hunch right now is that even though it maps, because it's a block spin variable, you should not literally think of them as a paramagnet when this term dominates. When this term dominates, yeah, let me not say anything. Yeah, intuitively, when this term dominates over this, you choose one of the states consistent with this on the plaquette. Like you take the limit when they're decoupled, you have one of the states, and all those states are degenerate states, right? But then once you couple them, whatever happens in one value of the ratio must happen in the other value of the ratio. So if we agree that for one particular side of the ratio, it is many-body topologically ordered, it must be. But then the caveat is that if we agree the other side is not topologically ordered, then the other side also must not be topologically. So I don't know what's the reconciliation there. But this is an exact statement. If you look just at the plaquette parity variables, the system will just look like a Z2 Ising gauge theory. So this is the new result, which is not in the paper. I'm writing it up right now. Right.
You put in some automation in Z.
Right. Right. It does not, in fact.
The topological degeneracy can be separable from other.
Right. Yeah, I agree. Yeah, something like that must be true. The other similar things we can say is that the plaquette parity variable is not really a variable. There's a projective structure. You have coarse grained away this additional finer detail, but this motivates us to do that. I need not pay special attention. However, having said that, all this won't be true, as you said. So even within this class, if I just take the two-spin model, nothing of this sort is true. The two-spin also has plaquette parity conserved operators, but that's why I went into this discussion of that this local structure is relevant. So you have to, and there might be further, phase diagram-like classifications possible. Okay, very good. We are doing fine. Now, I mean, this is all I generally wanted to, we have time till 1, na? Oh, okay. So I can now start. So this is all the, if you wish, the theorem level exact statements. The rest is all discussion. Maybe I can just wrap up in a few minutes, just say it in words without writing anything. So there is one, maybe for students, it might be interesting. So one might wonder as a student, like, yeah, please. Right, what? The tau variable. Right. It's like a many-to-one. So it's a projective structure. It's really a block decimation. You do one step of the block decimation, RG, if you wish. Gone. Indeed, precisely. So so this is more for the students that I was not motivated, but having said that, why it is interesting, perhaps for an expert, is this. I believe this anti-commuting algebra of the local conserved charges is something genuinely new. Okay, it does not exist. It is definitely not part of Levin-Wen models and that kind of thing. Okay, however, you can see that from this discussion, maybe this liquidity can coexist with many-body topological order. So what are the general consequences whenever we have this structure is a general sort of research questions. I have listed down possible questions you can ask. But having said that, it's only after the fact I have the sense that it is something new. It's not like I was trying to get this. I was not trying to break the commuting structures of local conserved quantities. But I would just like to quickly point out how I arrived at this general structure. So consider the following model. So this is a previous paper where I played a different game. And the game was follows, that you have, let's say, Jordan-Wigner fermions on these chains. How can you couple them and still sort of show that the Jordan-Wigner fermions survive in some exactly solvable sense? And the trick was you include an additional spin, and these spins interact with the chains only through ZZ couplings. So these are details. So these ZZ couplings are pure density-density interaction, and then all the tricks, Jordan-Wigner tricks, go through. But this particular model, so the different models now you can construct given this observation, you just put extra sites in between. This particular one has this extensive degeneracy, and I was like, what's going on? Why do you have extensive degeneracy? And of course, the answer is because this model has, students, please, the anti-commuting algebra. And this is the anti-commuting algebra. So the sigma z on these special sites commute, but the other one is you take a product of sigma x on these three sites, very similar. The one neighbor of this special site and the other neighbor also commutes. And you can see that they extensively number and then anti-commute. Right? So this was my first sort of introduction to this structure. However, this is kind of unsatisfactory from the point of view that if you have such commuting, such conserved quantities, we like to consider them as effectively classical variables. And that may or may not be satisfying. So I wanted to sort of find models where you don't have this kind of conserved quantities, site local. So more general, such that it is fully quantum mechanical. There is no effectively classical. And this led me to this. In fact, it first led me historically to the more elaborate model. And then I was talking to Ajit Balram, and I realized that this is a simpler way of doing these things. Okay, so that is something maybe, there's no reason to take some existing concept in the literature and trying to break it. You can just be playful and curious and, So with that, some additional remarks is actually these models have a hidden conserved quantities which all mutually commute, which I'm not writing down. They are non-local. That's the hint I will give. So then, because of this, extensive degeneracy and the block diagonalization, one would naturally start wondering if what would be the ETH, eigenstate thermalization hypothesis, and those kind of things in the context of these models. Okay, and this is what I would like to talk more with Shtitadi. But my hunches are that you have a lot of many-body density of eigenstates in the mid spectrum, and therefore, in some sense, ETH becomes true. And you have to make some assumptions, roughly speaking. But here I get that extensive density of states for free by the construction. Could that mean that there is ETH-like property, even going down to the lowest energies, thermalization? I don't know. That's a conjecture. Okay. By a very similar token, whenever you have a lot of degeneracies, you might start wondering, what are the quantum chaos related, like OTOC properties. So I've made some conjectures. And the recent realization, this was through a conversation with Benoit Dussault, is that, you see, we showed essentially that there is many-body topological order. However, there's this extensive degeneracy. And so why are we interested in Kitaev toric code? Fundamentally, okay, many-body topological order is interesting, but the Kitaev toric code is an RG fixed point type model. But of course, the quantum information community actually literally wants to implement that, right? So from that point of view, from a quantum information processing perspective, actually what my belief right now is that these models have something called, so there's something called stabilizer codes. The Kitaev toric code is a topological stabilizer code. There's something else called subsystem codes. These are Bacon, Shore. I'm not an expert. This is just a preliminary understanding. There's something called subsystem codes, where you try to absorb errors through some gauge-like physics. And this is a comment I didn't mention. This has a smell of some gauge, the local conserved charges, after all, but they're physical charges, right? So it's as if, in standard gauge theories, actually you mod out the gauge redundancy. You don't pay attention to that. You don't want to consider them as two separate states. So here it's kind of a counterpoint. Like you have made such a redundancy physical. That's one way of looking at it. And so therefore, the example of Litzou's theorem I mentioned in the beginning, so this cancellation argument, you can actually think of a physical manifestation of the Litzou's theorem. Okay. In any case, so you have topological stabilizer codes. You have subsystem codes where you try to absorb the bit flip, all these quantum informationally important errors in some gauge-like way through some degeneracies, and then you combine the two ideas called topological subsystem codes. This has been worked out by some people. If you're interested, I can write down the name of the person. So there's this idea of topological subsystem codes in the quantum error correction community. And I believe these codes, if you wish, from that qubit language, might actually be topological subsystem codes, which I'm trying to work it out right now. I guess that was my final comment. And thank you for your attention. Yeah. Yes, yes. No, that's a good point. So this I have not worked out in detail. I'm trying to work out. But if you are the competitive sort, just put this structure on a Kagome lattice and have 3-spin products or 2-spin Ising. You will see it will have also anti-commuting structure, but I mentioned this hidden commutants. That is not true, and it's not clear what will. Those two things will still be true. But what is the new stuff? No one knows, I think. Yeah. Yeah. Mm-hmm. Right.
But the extensive degeneracy also there is coming.
Example?
Like for the record also.
The degeneracy of 4.
That's only.
Okay. But yeah, this is true even on a torus. So that's how you should think about it. That's what I'm telling you. Even when you have no boundaries, it's true. Yeah, but yeah, maybe that detail I don't know about the record order. We can chat actually. Mm-hmm.
It also, like you mentioned, commented that it also gives us this topological degeneracy. That point
Topological. So the super selection quantum numbers Shuvik pointed out, right? They become operational for the 4-spin Hamiltonian. That's sort of, that does not imply degeneracy immediately, but you have this super selection business going on. Now the lowest energy eigenstate in each sector I'm claiming is degenerate. But there's that the existence of such super selection gives you a sense that maybe something is going on. So one other comment, first of all, the toric code, you get it as a perturbative limit of the Kitaev honeycomb model. And honeycomb model are 2-spin variants. So you can ask that question. Can you get this 4-spin model as some perturbative limit of some 2-spin models? It is a little elaborate, not very natural. So I'm not paying attention to it, but it's a nice exercise. The other nice exercise, which I plan to do, is as we discussed, this is a family resemblance to the toric code. You can add star terms on top of this. And then you can ask, is there some, there is this degeneracy, there is the star term excitations, which they will mutually commute. What does that mean? Yeah, let me stop here. Thank you very much. It was very helpful for me too. Till day after tomorrow, lunchtime. Yeah.